Good morning. Today we are going to start chapter 8, which is the main focus of before the first midterm. So we'll start from sequences. The sequences is simply just a bunch of numbers in a certain order. So there are, so a sec. Okay. So basically you have a bunch of number A1, A2, and AN, and there's an infinite number of numbers in this, well, in this list of numbers here. And they're written in a definite order. Infinite number of numbers written in a definite order. And this is a sequence. And usually we write it as the a brace and then AN in it, where AN usually has a formula and or some description of it. Sometimes we can even add subscripts and well, add a subscript and a superscript to describe where it starts and where it ends. So it will start from 1 and ends at infinity. So it's an infinite number, an infinite list of numbers, but it's written in a definite order. And for each term, you can consider it as a function, like as a function which whose domain is the set of all positive integers. So for example, AN, you can consider it as there is some function adds on the positive integer n. And the nth term is given by by this function and the positive integer. And for this list of the and for the sequence, the elements can repeat itself. Well, n elements can repeat. For example, the sequence 1 1 1. The list of number there has an all of its terms are 1 is also a sequence. So let's see a couple of examples. So usually the sequence is described by the function f of n, and for example, this sequence n divided by n plus 1, and from 1 to infinity. This represents a sequence where the nth term, this formula here always represents the nth term. So this sequence is the nth term of this sequence is given by n divided by n plus 1. And if you're plugging number in it, if you're plugging n is equal to 1, you get the first term in the sequence is 1/2. Second term is 2/3. And this n is equal to 1. This n is equal to 2. N is equal to 3 gives you 3/4, and so on. And as long as if you want to know any term in the sequence, you just need to figure out the order of the turn and then plugging that positive number in. And see another example. For example, cosine n pi divided by 6. And now if we start from 0, then this still represents the n term. An is still equal to cosine n pi over 6, the formula inside the brace. But now since this sequence starts from 0, so the first term in this sequence will be corresponding to the case when n is equal to 0. So that is 1, because cosine 0 is 1. And then when n is equal to 1, you get cosine of pi 6. That's square roots of 3 divided by 2. When n is equal to 2, you get 1/2, which is cosine pi thirds, and so on. But sometimes the sequence doesn't have simple formula. Like for example, if we want to define the sequence Pn, like for example, is the population of the world as of January the 1st in the year n. Then there's no formula for this sequence. You can only use the statistics that we have to determine all the turn from 0 to like this year's 2021. You can determine all the turn that's from 0 to 2021, but but for any n is greater than 2021, we have to wait until that day. And for a concrete example, when n is equal to 2021, this P 2021 is the population. As of January the 1st, 2021. And sometimes the formula, well, the turn in the sequence is given by recursive relation. The most famous example for this is the Fibonacci sequence. Where the recursive relation is given by f of n is equal to f of n minus 1 plus f of n minus 2. And this is true for n is greater than or equal to 3. And the first 2 points is given. F of 1 is equal to 1, f of 2 is equal to 1. And then use this recursive relation, you can calculate f of 2 is equal to f of n minus 1, which is f of 2. Wait, f of 3. When n is equal to 3, this is equal to f of 2 plus f of 1 is equal to 1 plus 1 is equal to 2. And f of 4 is equal to f of 3 plus f of 2, which is, this is 2 plus 1 is equal to 3. And you can continue to calculate all the terms in the Fibonacci sequence using this recursive relation. Since there's infinite number of turns here, and whenever there's an infinity, we are always interested in the limits of that infinite list. So So of course, we will be interested in the limits of the sequence, the limits of the sequence. And the limits of a sequence, it's basically, we want to find the term, we want to let n go to infinity and find which number is the sequence, which number the sequence is approaching. L goes as n goes to infinity, and right, and the sequence is an. Here, it doesn't matter which term you start. You can start from 2 or 3 or even 100, because we let n go to infinity. So any finite number, you can start from any finite number, any finite term in the sequence. And then if this limits exist, we say the sequence an converges. Or is convergence. Otherwise, we say it diverges. Or is divergent. So as I mentioned at the beginning of the class, an can be considered as a function f of n. So from here we can get a lot of limits laws for the sequence. And these laws are not that different from the laws you have learned from for the limits of the functions. So suppose we have two convergent sequence. So suppose an and bn, both sequences are convergent. And c is a constant. So then here we can think of an as the function f of n, and bn as a function. Bn is equal to to another function that evaluated at n. Then the limits of an plus bn as n goes to infinity. This is simply the limits as n goes to infinity of f of n plus g of n. And then from the limits laws for function, we know this is equal to the limits as n goes to infinity, f of n plus the limits as n goes to infinity, g of n. And then because f of n is equal to an and g of n is equal to b sub n, so this is equal to the limits as n goes to infinity, an plus the limits as n goes to infinity, bn. So then similarly, we can get the difference between the limits of the difference between the two sequences. It's equal to the difference of their limits minus the limits, using a similar argument. And then the scalar multiplication, the limits of the scalar multiplication of the sequence is equal to c times the limits as n goes to infinity, an. And then there's a product of the sequence. The limits of the products of the sequence is equal to the limit as n goes to infinity of an times the limits as n goes to infinity of bn.
Sorry, really quick, could you just go back one slide?
Oh, sure.
Thank you.
These are just from the limits of the functions. So basically, the limits of the sum is equal to the sum of the limits. The limits of the difference is equal to the limit of the difference of the limits. And then the limits of the scalar multiplication is equal to the scalar multiplication of the limits.
All right, I'm good.
Okay. And all these, in order to use all these formula, you have to have you have to ensure that both sequences converge. And then there's a product formula, which is also from the function, the limits of the functions. And then, of course, there will be a formula for the division, an divided by bn is equal to the limits as n goes to infinity of an divided the limits as n goes to infinity of bn, provided that the limits of bn as n goes to infinity is not equal to 0, because you can divide a non-zero number by a 0 number. There are two cases when the limits of bn is equal to 0. So note, if the limits of bn is equal to 0, first case is that the limits of n goes to infinity an is not equal to 0. Then, so this limits exist. That's the that's what we have to ensure at the beginning. But it's not equal to 0. Then in this case, this is equal to the limits as n goes to infinity, an divided by bn is equal to positive infinity if the limits of an is greater than 0, and is equal to negative infinity if the limits of an is less than 0. It's an. So basically, it's a positive number divided by 0, or it's a negative number divided by 0, which gives you plus infinity or negative infinity, respectively. And then if it's equal to 0, then basically we want to calculate the limits of the function f of n divided by g of n. Since at the beginning we assume an is equal to f of n and bn is equal to g of n, then this will become a 0 divided by 0 in determinate form, and then we can use the L'Hopital's rule. We'll see an example later. Then, right. Then we have another formula. This is for the power. The limits of an to the power p as n goes to infinity is equal to the limits, the power of the limits. And this is, of course, requires p is greater than 0 and an is also greater than 0. Then there's one more. So this is a special case. N goes to infinity of c. This is equal to c. And this expression here just means we are taking the limits of some sequence, but all the terms in the sequence is given by the same number c. So in function sense, you can consider this as a constant function. So we can call it a constant sequence. So all the values of an are the same number. So we have been emphasizing the sequence as a function, and there's a theorem to describe the limits of the sequence and the corresponding function. So sequence as a function. So if the limits as x goes to infinity, f of x. So if this limit exists and an is given by the value of the function evaluated at positive integer, n is a positive integer, then the limits of an as n goes to infinity is equal to the same limit. This theorem basically tells you that if in the future you are interested in this in the limits of the sequence, you can try to find the you can try to find a function that's corresponding to this sequence first, then study the limits of that function. But so know that if the limits of an goes to infinity, so the converse of this theorem, if this limits exist and an is equal to f of n, then the limits of x goes to infinity, f of x is not necessarily L. So the converse is not true. And an example of this, you can consider, let's see, you can consider the psi function, the counterexample for the converse. You can, for example, you can consider, let's do the sine function. So suppose we have a sine function. Y is equal to sine of x. And if we let an is equal to sine of n pi, then a0 is 0. A1 is also 0. A1, A2, A3, A4, So you can see all the terms in this sequence are 0. But and so then so the limits of this sequence exist is equal to 0. N is equal to 0. But the limits of sine of x doesn't exist as x approaches infinity. This doesn't exist because it's oscillating. Any questions so far?
Can you go back one slide real quick?
Sure. So I do post the lecture video after the class, after the recording is finished.
Thank you.
Right, and this counterexample. But this is just a warning. Usually we won't use the converse. This is the converse of this theorem just tells you if you find the limits of f of x doesn't exist, then the limits of the function doesn't exist, then you probably need to try another way. It doesn't mean that the limits of the sequence doesn't exist either. Right. Anyway. So let's see 2 examples on using this theorem. So for example, if we want to calculate, should be 2. Right. If we want to calculate the limits as n approaches infinity, n divided by n plus 1, suppose we want to calculate these limits, then the first thing you can do, or you should do, is to try to see if the limits, when you replace n with x, try to see if this limit exists. And for this limits, you can easily calculate it's just equal to 1. You can use either the L'Hopital's rule. This will be an infinity. There are two methods you can use to calculate this this limits. You can either use the L'Hopital's rule, which is straightforward. And when x approaches infinity, this is an infinity over infinity indeterminate form. So then you take the derivative of the top and the bottom, you get 1 divided by 1, so the limits is equal to 1. Or you can do you can do what we have done for the limits involves infinity. You can divide both the top and the bottom by the highest power or highest degree term. So in this case here, the highest degree is x. So divided both the top and the bottom by x, 1 over x. And you get this the limits as x approaches infinity of 1 divided by 1 plus 1 over x. Then when x goes to infinity, 1 over x goes to 0. So you get this is equal to 1 over 1. So it's equal to 1. And from here, we know that the limits of the function exist. When the limits of the function exist, the limits of the corresponding sequence also exist and is equal to the same limits. So this will also be 1. This is 0 here. So let's see another example. Now, this time, let's try to calculate the limits as n approaches infinity of natural log of n divided by n. So again, to calculate the limits of this sequence, we should try to first see if the limits of the corresponding function exist. So we will rewrite all the n. We will replace all the n by x, and then yeah. And then if we look at the function, when x goes to infinity, natural log of x goes to infinity, and x, the denominator, also goes to infinity. So then this limit is actually a infinity over infinity indeterminate form. Indeterminate form. Right? So we can use the L'Hopital's rule. So this limit is equal to the limits as x approaches infinity, natural log of x prime divided by x prime, n is equal to the limits as x approaches infinity, 1 over x divided by 1. So it's equal to the limits as x approaches infinity of 1 over x, which is 0. So then since the limits of the function exist, the limits of the corresponding sequence should also exist, and is equal to the same limits, 0. Any questions so far? Okay. But we can always use the L'Hopital's rule. For some sequence, it's impossible. For example, if we want to find the limits as n approaches infinity of -1 to the n power divided by n, then no, I didn't miss anything. Then if we want to find the limits of this thing, then right, if we still try to use the corresponding function, you will get the limits as x approaches infinity, -1 to the x divided by x. And -1 to the x is not well defined for every x. So basically, you can think that this function is not defined everywhere, or it's not well defined. This function is not well defined. So in another word, it's the value of this function doesn't, you can't evaluate this function at any point. But if you just look at this sequence, let's try to find the first few terms. When n is equal to 1, let's see, let's make a table here. So let's use 2 columns. The left column represents the value of n. The right column is the value of the sequence. So when n is equal to 1, this guy is equal to -1. When n is equal to 2, this guy is equal to 1/2. When n is equal to 3, this guy is equal to -1/3, 4. And then let's don't do 4. Then if you keep going, like for example, n is equal to let's do 10,000. Yeah, 10,000. 10,000 should be 10 to the 4. Then an is equal to -1 to the 10 to the 4. 10 to the 4 is an even number, so it's equal to 1, and the denominator becomes 10 to the 4. And then if you keep going, you realize that the absolute value of -1/n, this guy goes to 0. This guy is equal to 1/n, and is 1/n, and goes to 0 as n approaches infinity. And all this sequence do is basically it's basically just oscillating with respect to the x-axis. Right, n is equal to 1 is equal to -1. Basically, it's just oscillating, but with a smaller and smaller magnitude. So then eventually, this guy will go to will get closer and closer to the x-axis. Right. So this is A1, A2, A3, A4, A5, and so on. Eventually, when n is large enough, an will be close enough to the x-axis. The only difference is that there's a -1 to the n, but it doesn't matter because the magnitude is getting smaller and smaller. So from all these intuitions here, we can conclude that the limits n to the infinity, as n goes to infinity, of -1 to the n divided by n should be equal to 0. Yeah, and it's actually equal to 0. And there is in math, there is a very articulate proof of it, but we are not going to do that in this class. And this is actually part of another theorem. So, and this theorem works for a special case of the sequence. Let's see. So suppose we have a function a to the n, a sub n. If the limits as n goes to infinity, an, the absolute value of an is equal to 0, then the limits of an, the original sequence, is also equal to 0. So in this case here, an is equal to, in the last example, an is equal to -1 to the n power divided by n. The absolute value of an is equal to 1/n. And since this limits, the limits of the absolute value sequence exists and is equal to 0, it must be equal to 0. If it's equal to 1 or something else, then the limits may not exist. But if it's equal to 0, the the limits of the absolute value sequence is equal to 0, then the limits of the original sequence is also equal to 0. Any questions?
Yeah, so I'm still a little confused on why the limit when it's in the x terms wasn't defined, but then the n was in this instance or this last example.
So for example, if we want to calculate -1 to the square root of 3, then this guy is not well defined. There's no, I think for a negative number, there's no like a irrational power for the negative number because the sign is a problem.
But why would it be the square root of 3 instead of just like 3 if you're plugging in like?
But when you consider it as a function, when x goes to infinity, you will see a lot of irrational number.
Oh, okay.
Yeah, for function, it has to be defined like at least x is greater than 0 for all x is greater than 0. And because it's not well defined everywhere, especially at those irrational points, we can take the derivative of it. We can use the L'Hopital's rule.
Oh, okay. So it's mainly just because of the irrational points it doesn't work very well.
Yeah.
Okay, thank you.
Any other questions? All right. Right. Let's end with another famous example, the geometric sequence. So here, the sequence r to the n power is convergent if the absolute value of r is less than 1, which is equivalent to r is between 1 and -1. Right. Less than, well, it's not exactly this because we have to consider the endpoints. So this guy is convergent when r is less than or equal to 1 and greater than -1. And divergence for any other r. And in particular, the limits as n goes to infinity, the limits of this sequence is equal to 0 if r is between 1 and -1, and is equal to 1 if r is equal to 1, and is divergent for other values of r otherwise. This is the conclusion of the last theorem. Let's give you a sketch of the proof. So this is the direct results, direct results of this theorem I presented earlier here. So in this case here, for geometric sequence, when the absolute value of R is less than 1, then let's start from a positive R. If R is positive or is non-negative, then R to the n, limits as R. As n goes to infinity of R to the n is equal to 0 if R is between 1 and 0, because this will be corresponding to a power function. This will be corresponding to a exponential function. So in this case here, R to the n, if we consider it as a function, this is R to the x, and R to the x is is an exponential function. It is decreasing to 0. It has the x-axis, it's horizontal asymptotes, and it's decreasing if R is less than 1, greater than 0. It's increasing if R is greater than 1. So in this case here, when R is greater than 0, less than 1, when R goes to infinity, the infinity is the positive x direction. Well, x goes to infinity is the positive x direction, then the limits of R to the x goes to 0, which means the limits of R to the n also goes to 0. And two trivial case is that when R is equal to 0, this is also equal to 0, because all the term in the sequence will just be 0. When R is equal to 1, all the term in this sequence will just be 1. So the limits of R to the n is equal to 1. And when R is greater than 1, then the exponential function is increasing, and as x approaches infinity, this exponential function will also approaches infinity. So we say it's equal to infinity or divergence. When R is greater than 1. And this is the case for positive R, for non-negative R. If R is a negative number, R is negative, then if the absolute value of R is less than 1, then the absolute value of R to the n goes to 0 as n approaches infinity. This is corresponding to this decreasing exponential function here, except now the base becomes the absolute value of R. So this goes to 0. So then from the theorem, so that's R to the n also go to 0, also goes to 0 as n approaches infinity. Then if R is the absolute value of R is equal to -1, is equal to 1, which means R is equal to -1, then -1 to the n power as n approaches infinity, this doesn't exist, because it will just be an oscillating sequence. When n is equal to 1, you get -1. When n is equal to 2, you get 1. A1, A2, A3. Then it will just keep oscillating between -1 and 1. If R is greater than 0, if R is less than -1, which means the absolute value of R is greater than 1, then the sequence will also be oscillating, but the magnitude is getting larger and larger. Then, right, A1, A2. So then in this case, this is also divergence. Right. Any questions? Okay, we'll meet tomorrow.
Thank you.
Thank you.
Yep.